Hess's law, which you have already studied in general chemistry, simply states that enthalpy is a state function. In other words, the change in enthalpy is independent of the path taken from the initial state, here the reactants, to the final state, here the products of a chemical reaction. Let us consider a hypothetical reaction denoted by star between 1 mole of A and 2 moles of B to form 4 moles of X and 5 moles of Y. Let us assume that we can achieve the same result as in equation star going through a different path shown by the 4 steps identified in blue. Hess's law states that since H is a state function, the change in H between reactants and products through the yellow path is identical to the change in H through the blue path. Hence, delta H for star is equal to the sum of delta H for reaction 1 plus reaction 2 plus reaction 3 plus reaction 4. As an example of the application of Hess's law, let us consider the alcoholic fermentation of glucose. This reaction is simply written as the transformation of 1 mole of glucose into 2 moles of carbon dioxide plus 2 moles of ethanol. Let us show that this fermentation reaction can be written as the combination of the combustion reactions for glucose and for ethanol. The combustion reaction for glucose, reaction A, is written as 1 mole of glucose, solid, plus 6 moles of molecular oxygen, gas, to yield 6 moles of carbon dioxide, gas, plus 6 moles of water, liquid. The standard combustion enthalpy of glucose at 25 degrees Celsius has a value of minus 2,808 kilojoules per mole of glucose. The combustion reaction for ethanol, reaction B, is written as 1 mole of ethanol liquid plus 3 moles of oxygen gas to yield 2 moles of carbon dioxide gas plus 3 moles of water liquid. The standard combustion enthalpy of ethanol at 25 degrees Celsius has a value of minus 1,368 kilojoules per mole of ethanol. The fermentation reaction requires 1 mole of glucose as a reactant. This could be achieved using reaction A as written, since ethanol appears as a reactant in that reaction with 1 mole. The fermentation reaction also requires the formation of 2 moles of ethanol liquid. This could be achieved using twice the reaction of B, so we would have 2 moles of ethanol. Indeed, twice the reverse of reaction B, which we could call as minus 2B, is written as 4 moles of carbon dioxide plus 6 moles of water liquid to yield 2 moles of ethanol liquid plus 6 moles of oxygen gas, with a standard reaction enthalpy of minus 2 times minus 1,368 kilojoules per mole, or 2,736 kilojoules per mole. So this would suggest that we may be able to write the fermentation reaction by combining reaction A with the reaction minus 2B. Let us check whether this is correct or not. We first rewrite reaction A and reaction minus 2B and add these two reactions together. Then cancel out substances that appear as products and reactants. So, for instance, we can cancel out the 6 moles of molecular oxygen gas and the 6 moles of water liquid, which appear on both sides of the reaction equation. We also simplify the 4 moles of CO2 on the reactant side with the 6 moles of CO2 on the product side. After simplification, the equation resulting from the addition of reaction A with reaction minus 2B is shown to be identical with the fermentation reaction star. Hence, the standard enthalpy of formation of glucose must be equal to delta RH standard for reaction A plus delta RH standard for reaction minus 2B. That is minus 2808 kilojoules per mole plus 2736 kilojoules per mole, or minus 72 kilojoules per mole.